get your minds off of lunch and back into engineering. And it's my great pleasure to start this session with Dr. Axel Meisen. And this is a panel on fusion and fission energy. So I will, Michel Laberge is going to be coming in over the Zoom. Bibake and Igor are here on stage, and we're going to have a really interesting discussion. Axel will explain a little bit the links of the things that are going on here, but this is about all things fission and fusion and where we're going in Canada. So, Axel, thank you so much.
Thank you very much, Robert, and I'd like to call the panel then into session. Let's see. If I click something, does something happen on the screen? Okay. There. That's the first one. Perfect. So thank you very much for joining us here this afternoon. The short title of this panel discussion is Fusion and Fission Energy. There's actually no such thing as fusion and fission energy. There's energy that is derivable from fusion and fission phenomena, but we tend to shorten it just as fusion and fission energy. I'm joined by three panelists whom I will introduce ad seriatim as we go through the panel session. Let me just say something. So let me set the stage by introducing our speakers, including myself. I'm Axel Meisen. I'm the president of the Fusion Energy Council of Canada. This is a group of women and men dedicated to looking objectively at the development and the deployment of energy derived from fusion phenomena in Canada. So that's really what we are about. I want to underscore the word objective assessment. We're not an advocacy group, although some of us feel that way from time to time. But I think it's, as engineers and as scientists and as responsible citizens, it's really important to be objective in our assessment of opportunities, which means looking at all the benefits, but also looking at the downsides that are associated with it, technically, financially, economically. I think we all know that energy is fundamental to modern life. We've heard it this morning, and we've heard it repeatedly. And often we tend to think about this just in quantitative terms, you know, how many kilowatt hours are needed. But there's a very human dimension to energy in terms of energy's use. And I just point to the fact that the world population is rapidly increasing. We will probably be near 10 billion people within a decade or two. Canada just has passed the 40 million mark. And modern life requires energy in order to be enjoyable and be functional in all regions of the world. Of course, energy is also associated with problems, at least the way we have been producing energy. So there are issues about the sources of supply of energy and how to utilize it. There are different ways of accessing energy, and one of the most potent ways is to derive energy by converting mass. Mass, translating mass into energy, and all of us, I think, remember Einstein's formula, E is equal to mc squared, is indicative of what phenomena that are associated with changes in mass are about. And both fusion and fission, as will be explained by our first two speakers, and the third one from a fission point of view, are associated with making changes to the core of atoms, which is the nuclei, and convert them so that there is a change in mass. The panel's objective, and the objectives that we have set ourselves for this panel, is to give you an introduction into the phenomena of fusion and fission. But my real hope is, and I think it's the hope also of our panelists, is that we can seed in your minds some questions that are worthwhile looking at with respect to fusion and fission development, and not just pose the question in our minds, but also start thinking about the answers to the questions. So we're trying to make this into a creative panel, and I'd like you to leave this panel later on today thinking, I learned something or I saw something which triggers in my mind of maybe how we can do that. So I will call on our three panelists to give us about a 15-minute overview from their perspective, either on fusion or on fission. We'll then have a few questions amongst us as panelists, and then we'll go to you as the audience to see what questions or challenges you might have. So, if I may then bring in Michel Laberge, who should be joining us via Zoom. Michel is the founder of General Fusion. It's a company which is based in British Columbia, in Vancouver. I think it started in Burnaby, but it's located in the greater Vancouver area. And Michel will talk about General Fusion's fusion concept and the importance of different types of technologies supporting fusion development and ultimately deployment. So if I may call on you, Michel.
1, 2, 3. Do you hear me, guys?
Yes, we can hear you.
All right. Okay. So I'm Michel Laberge. I'm the founder and chief scientific officer at General Fusion. We're in Vancouver. We're about 100 employees right now. We've been around for like 20 years. So I'll give you a little spiel on fusion first and our particular source of fusion, and then what we need to build this. So you're probably all familiar with fission. That's the normal way of making energy in the present-day reactor. You shoot a neutron at a big nucleus, like uranium, split in two, makes a couple more neutrons. The neutron hit more uranium, chain reaction, energy, very nice. However, there are two parts, barium and krypton here, but they're all over the element. So you have radioactive waste, and people are not totally realistic about it. They're scared of radioactivity more than they really should. So because people are a bit hysterical about radioactivity, fission haven't got the acceptance that it should really. It's an excellent good way of making energy, but it's not accepted very much because people are not totally rational about the acceptance of radioactivity. So what can we do? There's another way to make energy from nuclear reaction, and it's fusion. Fusion is the reaction inside the sun and all the stars. It involves putting two hydrogen together to make helium. Now, on Earth, if you want to do that, the reaction that is used to do is deuterium, tritium, make helium plus a neutron. You can count the proton, neutron here. You can see it's the same. But at the end there, the mass is about 4% less. So there's 4% of mass turned into energy. This is a nice reaction. It doesn't produce any radioactive waste, produce helium, party balloon. However, the two reactant, the two nucleus, are positively charged. So two positively charged things repel each other. So in order to fuse, you have to throw them at each other with very high speed. Speed equals temperature. And if you want this thing to fuse, you have to cook it to 100 million degrees C. Now, 100 million degrees C is rather hot. You cannot put that in a pot, otherwise the pot will melt. So what people have tried to do in the past is to make a magnetic field. You put a couple of coils in the donut shape, make a magnetic field. When you heat the gas at those temperatures, the collision between the atom is so brutal that the electron and the ion get split apart. So what you end up is a big soup of ions and electrons called a plasma. And the electron and the ion, they circulate around, they spiral around the field line, as you can see here, and they go around and around the donut. They never touch the wall. Then you try to heat that up by throwing neutral beam, radio frequency. You pass a bit current in there to make heating, and you try to get that to 100 million degrees C, make some fusion, make some energy. And that's where most machines that study fusion are made. It's called magnetic confinement fusion. This is the inside of the JET, the Joint European Torus in England. Those guys have achieved maybe 0.5, like about half the energy of fusion than the energy they put in. Right now, there's a bigger machine built in the south of France called ITER. It's a collaboration between all the country. And that one should make more energy of fusion than the energy you pump in the machine. However, it will not put electricity on the grid. And that will start making DT reaction in 2035, although the project's a bit late right now. And it will produce power plant from that expected in 45, 50. So that's a bit of a long project. That's one way of doing it. The other way is the laser fusion. You fire a laser at a ping pong ball. Inside the ping pong ball, you put deuterium tritium. The laser explodes the wall. It implodes the fuel. When you compress, something gets hotter, adiabatic compression. So if you compress it really, really fast, it gets really, really hot. And those guys have managed to achieve a good shot of fusion just last fall, actually. They managed to do about 3 million joule, 3 megajoule of fusion energy out of a 2 megajoule laser, which is pretty good stuff. However, to make 2 megajoule of laser, you needed 300 megajoule of electricity. So they're still not quite to making electrical power plant, but that was a good demonstration of that fusion can get going. But they're getting closer. This is a shot of the laser hitting a little pellet. The biggest machine is the National Ignition Facility. That's in Livermore. There's a 2 megajoule laser there that's about the size of a football field that focuses the energy on those little pellets. Now, most people think fusion is useless, never done anything, will never do. However, if you look at the progress of fusion, which is red dots, it has gone about 10,000 times more fusion now in 2000 than in 1970. And the rate of fusion that they achieve in those machines is as much as the number of transistors on a chip, the very famous Moore's law. So the progress of fusion was tracking Moore's law for the longest time, except now there has been a bit of a shift to the right. You can see the NIF and the ITER dot there. They're going to the right because those machines are quite big. So in the past, the machine was smaller, but as the machine got bigger and bigger, it's cost more money and it's difficult to raise the money to do it. So the progress has stalled a little bit over the last couple of decades. But you can see that fusion have done great progress since the 70s. So as I say, on the left here, you have magnetized fusion. This is the way it is usually done. Some people try the laser fusion. On the right, general fusion, we want to do a mix of the two. We want to have magnetic field to hold on the plasma, but we also want to compress. Now, when you have a magnetic field, it prevents the particle from escaping, so the heat loss are not so fast. So you can compress slowly. The laser guy, they have no magnetic field. The heat escapes very, very fast, but with the laser, they can compress in about 1 nanosecond. It's 1 billionth of a second. So even if the heat escapes fast, it can still win because they compress so fast. With a magnetic field, we can compress slower. And slower allowed us to use liquid metal and piston with steam, which is a much cheaper technology than laser beam. And also the DC guy, the magnetic field, they want to use superconducting coil, which are also very expensive. So the two technologies that are being investigated mostly are very expensive. And at general fusion, we think that mixing the two, we can do a little bit of a better job. So what we want to do is we want to spin a drum, put some liquid metal in it. It's going to be lead lithium. The centrifugal force push all the liquid on the wall. Then we inject plasma inside this cylinder. And then we have steam pushing on piston that push on the liquid and it implodes. So all the liquid get compressed in the center. At peak compression, it gets hot enough for fusion. The neutron flash comes out. All the neutrons get absorbed by the liquid metal. We're covering all angle with, like it's totally surrounded by liquid metal at the time of fusion. So all the neutrons are absorbed by the liquid metal. The liquid metal gets hot. We pump that continuously. Like this is a machine that shoots repeatedly about 1 time per second, but we pump the liquid continuously, goes in the heat exchanger, makes some steam. Some of the steam push on the piston. Some of the steam run on turbine, make electricity the usual way. So that's what we want to do. Now, the advantage of this thing is one of the big problem with fusion is actually the 14 MeV neutron, very fast neutron. When that hit metal, it destroys the metal. So the metal rapidly gets destroyed. So the tokamak and other machines that have a metal wall facing the plasma, they have a big problem. Their wall is going to get shredded in a few months. So right now, most tokamak are totally jammed because if it ever make enough neutron to make energy, the wall will get disintegrated. Their typical solution to that is to hope that in the future, somebody will develop a metal that will be better at receiving the neutron. I've been observing that for the 20 years, and the progress on the neutron resistance of the metal have been non-negligible, but quite small compared to what they need. So I think it's going to be a long time before they can find a metal that's good enough for that. The other thing is to make the fuel. So deuterium is stable. It's a nitrogen with an extra neutron. There's 1 part of 5,000 of all the hydrogen are like that. So in the ocean, where there's lots of hydrogen, you can extract this deuterium. It's usually extracted as AV water. You might have heard the term. You electrolyze AV water, and boom, you get deuterium. AZ, cheap, plenty. Tritium is a bit more problematic. It's radioactive, 11-year lifetime. There's no natural tritium. So you have to rebreed it. Typically, this is done by lithium component outside the machine. When you have the fusion, the neutron fly out. The neutron hit the lithium. It breaks it in two. It makes an helium and a tritium. You extract the tritium, shove it in the machine, and away you go. So this is called rebreeding. Now, in a tokamak, they lose a lot of neutron because they have lots of antenna and space and metal. So they lose too many neutrons, and they have a hard time making enough tritium to make the cycle go. At general fusion, we have 4 pi coverage with 2 meters of lead lithium. That absorbs all the neutron. The lead, sometimes when you hit the lead with a neutron, makes 2 neutrons. It's called neutron multiplication. So we actually have a breeding ratio of 1.4. So for each fusion that we make 1.4 tritium, which is enough tritium to keep the cycle going and enough tritium to extract to start the next machine. This is very good. And all the other business guys, they have a hard time getting enough tritium to get their cycle going. Also, there is energy extraction. You have to extract the energy from those fast neutrons. Other machine, the neutron hits, they want to put some blanket with some liquid in there to absorb the neutron and make some steam, just like us. However, lots of neutron is lost in the metal and in the antenna and the neutral beam. So they lose a lot of neutrons. So their efficiency of converting the neutron into heat is not so good. We have 4 pi coverage. At time of peak fusion, we have liquid lithium, lead lithium everywhere, and it catches 100% of the neutron. Then we pump that and make some steam. So we're good at energy recovery. Finally, our machine is cheap. It involves like steam, piston, seal, same sort of technology that you have under the hood of your car, piston and rings. We don't have superconducting coil, which are very pricey. We don't have laser, very pricey. We don't have neutral beam, RF heating, lots of exotic, expensive material device that goes into the normal fusion machine. Ours is very low tech. So when we do the economic of that, it allows us to come at a good number. So now we don't only need the fusion machine. If we want to do the fusion machine will run. The lead lithium will go in a circle. You will have to extract the tritium from the lead lithium. So it makes tritium, but the tritium is dissolved in the lead lithium. So you need a tritium extraction system. Then you need to store this tritium for the next shot. You need to top it up with some deuterium. You need to clean it. Like the tritium will also pick up hydrogen from the metal. So you're going to have a mixture of hydrogen, deuterium, and tritium. So you will need separate isotope separation to get the deuterium and the tritium and throw away the hydrogen, the proton, because that doesn't fuse. Also, the chimney, like all this deuterium, tritium, those processes will leak a bit of deuterium, tritium. You can only leak a very small amount of tritium because it's radioactive. So cleaning the stack and the water, like detritiating the air and the water coming out of your plant, it's a big deal. Heat exchanger, like standard heat exchanger, but that's involve liquid lead lithium on one side and steam on the other. That's a bit problematic because the tritium time to diffuse through the heat exchanger goes in the water. Pulling the tritium out of the water is very difficult. So you may want some coating on the heat exchanger to prevent the tritium from leaking out. Alternatively, sometimes we think that in place of a steam cycle, we could do a helium cycle, like a helium turbine. Because if the tritium go in the helium, it's actually easy to remove. But if the tritium go into the water, now that's hard to remove. But typically, our normal plan is with water, but it could conceivably be a hydrogen turbine. And then you have the turbine, make some electricity. Some of the steam straight out of the boiler go and push on the piston. Some of the steam spin the turbine. So all those items here are typical power plant device. Like, getting rid of the waste heat and everything. Some of the electricity is used to reform the plasma, but the fraction of the energy in the plasma is small compared to the compression energy. Typically, it's more be like, 50 megajoule of energy to make the plasma and 500 megajoule of piston energy. So about 10% is electric and 90% is steam. I like the steam recirculating energy because there's not too many hardware in the way, because hardware costs money. Like if you turn electricity, you charge capacitor, you fire a laser, you lose efficiency at each step, and it costs money. Here we put the steam right on piston, so the efficiency is good and the cost is low. So you have to develop all those alternate technology. At General Fusion, you were interested in making the fusion bit on the left, the fusion island, but the balance of plant and the conventional island, we're not very interested in that. So we would like to contract that out to some people that know something about tritium, know something about heat exchanger, know something about turbine, because really we don't know any of those things. So all those bits of technology we will need, and this is not exclusive to General Fusion. A lot of the other fusion, most fusion wants to do deuterium tritium. There's some company that wants to do advanced fuel, so-called advanced fuel, because they don't like the neutron and the tritium, like the neutron destroy the machine. So they want to fuse stuff that does not produce neutron. It's harder to fuse those things. For example, there's deuterium helium-3 you could do, but helium-3 is hard to find. And deuterium helium-3 is harder to fuse than deuterium tritium. People also have proposed boron, proton boron 11. Again, it doesn't make so many neutrons, but it's much harder to fuse those advanced fuel. So at General Fusion and most fusion company have selected to do the cheapest fusion, which is deuterium tritium. So all this extra thing, the detritiating, rebreeding the tritium, turbine, steam, blah, 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 heat exchanger, most people that do deuterium tritium will need all this equipment. So not only General Fusion will need that. And what have we done so far? We have worked on the plasma injector, like the thing on the top of the tank that injects the plasma. That works good. We've finished those. We've worked on compression system. This compression has to be nice and symmetric and fast. So we build those pistons. We push on liquid metal. This was a lead loop here. And we have managed to compress that with good symmetry, good speed. We have done some explosion where we put plasma in this aluminum tank here. We put some high explosive around it. So all the equipment is in container. This tank is on top, put some explosive, compress it. When we did that, the plasma go all squirrely, which can be seen on the right-left picture. This is a different magnetic field at different toroidal position. But after understanding why it goes unstable and working on it for a few years, we managed to get implosion that the plasma stays symmetric, the temperature heat up, and the neutron yield per second, the neutron rate, increase during the compression. So we know how to form the plasma, we know how to compress it. We had done some scale explosive compression. Now we want to put all those bits together and make a big implosion system to go with a big plasma, and then we try to go into the condition that we would need for a power plant. This will not be a power plant, this will be a low repetition rate machine, like 1 shot per week or something, but it's going to be a machine that will bring us in the condition required for a power plant. And that's the end of my talk. Thank you very much.
Well, thank you very much. Michel, and congratulations for having taken the company to this point. We'll be able to put some questions to you later on, but in order to keep on time, I'd like to invite Bibake Uppal now to give us his presentation on fusion from the perspective of a company called Kyoto Fusion Engineering. And you guessed it, it's of Japanese origin, but with growing roots here in North America. So your slide presentation can actually be seen there.
Perfect.
Okay.
There you go. Perfect. All right. Thanks, folks. As Axel mentioned, my name is Bibake Uppal. I work for Kyoto Fusioneering. Actually, we combine the words. It's a common word in the fusion community, but it can be confusing for people that haven't heard it before. We are a fusion plant engineering company. So Michel actually alluded to systems that go outside of the plasma core, the fusion core. And that's exactly what we're working on. We're building off decades of research at Kyoto University. Japan is uniquely positioned here because they have, in contrast to the US, they have been working on these plant systems for quite some time and support ITER with those systems, whereas the US is predominantly focused on the plasma physics. And so very complementary, and that's kind of the position of our company. I'll touch on my company a little bit more later on, but kind of what I want to cover is first the backdrop, kind of why fusion's needed and the value of it, the current state and how the industry has evolved, and there's been some fundamental changes. The joke of fusion's 30 years away, and it always will be. I mean, I hope it's not true, but I think there are some fundamental changes that have occurred that kind of break us out of that paradigm. and I'll walk through some of those. And then finally, I'll give some insight into what KF is up to, and hopefully spark some interest from some of you in either getting involved yourself in fusion, or at least becoming more familiar with what's going on, or encouraging others to do the same. So the backdrop comes as no surprise to any of you, but our challenges with energy are many. There's of course climate change, CO2 emissions, and the need to reduce that to net zero by 2050. Energy poverty, there's still a large portion of the world that lacks access to electricity or a clean source of cooking fuel. The WHO has said that the largest single health risk in the world is indoor air pollution, and there's a large chunk of the world that has to deal with that on a regular basis. Energy insecurity, so the countries that do have energy, and of course you've heard of the US in the news on this topic, but rolling blackouts and a lack of consistency in the grid. And energy dependence, I think the most pertinent example of this is Russia and the invasion into Ukraine, and how that's affected the energy going into Europe. And so Europe is very kind of desperate here to get a source of energy that is nationally sourced and not dependent on others. All of this is important to solve, but in parallel, we're dealing with an increase in demand. The Energy Information Administration released this, expected 50% increase in energy demand between 2020 and 2050. But to be honest, we should actually look to exceed this and strive for an environment of energy superabundance, where we can actually move that large swath of people in the world that lack access to energy and modern technology over to the right, and bring the folks like us that are up on the right down towards low emissions. That's kind of where we want to be, where that arrow is pointing now. Easier said than done, but worth at least striving towards. And so how do we get there? What would be the ideal energy source? You want it to be dispatchable, something you can turn on and off. Clean, of course, no CO2 emissions, or even ideally negative CO2 emissions. Geographically independent. Sustainable, it's a source of energy that isn't going to run out anytime soon. It can help decarbonize more than just electricity. It's safe, economical, and energy dense. And I argue, and it's not just me, that fusion checks all of these boxes, and then some. Of course, the economical piece needs to be determined still. We can't really extrapolate out from where we are now, but that'll be dependent on how we design and engineer these systems, and the regulation side as well, how kind of burdensome those are. I won't go into each one of these, but fusion is considered the holy grail of energy. That's not to say it should be our only energy source, so we should put all the eggs in that basket. There's a lot of good options out there, including fission, which we should look to kind of maximize our use of in the near term. But fusion is what we should be striving towards as well. It is manufactured, not mined, and is something that we can create anywhere in the world, with the main kind of ingredients coming from seawater. So it's the fundamental source of energy in the world. It's what in the universe. It's what the sun and the stars derive their energy from. And in a world with fusion, I mean, here's kind of just a graphic of what the energy grid could look like with fusion. But it enables a lot in a world of energy superabundance, where we have more energy than we know we can do with. It's hard to imagine what that world looks like. It's a world of science fiction. Vertical takeoff and landing planes, and the Hyperloop. You hear a lot about that. The superorbital point-to-point travel, which SpaceX talks about. These are all things that sound very far off and somewhat unlikely. But if we have more energy than we know what to do with, the things that we can dream up are limitless. We've always, throughout human history, thought through the lens of energy being a resource that we don't have a lot of, but this will kind of fundamentally change things if we are able to achieve fusion. So where are we at with fusion? There's a new paradigm, as I mentioned off the top, that is fundamentally different than what's been done in the past. Historically, it's been it's been an endeavor that has been pursued in the public sector, in the academic context, And Michel made reference to ITER in the south of France. This is a, tens of billions of dollars, if not hundreds. I don't have the numbers on hand, but a huge project which has been a cornerstone and something that has been great for the fusion community, but it's too far off. The timeline keeps getting pushed. There's a lot of cooks in the kitchen. It's inefficient. The incentives aren't necessarily there. It's not necessarily the path that's going to lead us to commercial fusion anytime soon. However, what it has allowed is supply chains to develop, for research to be done. Japan, for example, the reason a company like ours can exist is because there is a supply chain there, and I'll touch on that a little bit later on, that can support commercial fusion because it was developed to support public programs like ITER, JET, Michel referred to as well, in the UK, the National Ignition Facility, which of course a lot of you probably heard of the quote-unquote shot that was heard around the world. But that was the laser fusion in Livermore, US, and then JT60SAs in Japan. So these are the public programs, and there's more that have historically been where fusion is relegated to, or at least that's kind of the only place fusion has existed. But things have changed dramatically over the past mainly 5 years, but more so over the last couple of years. This graph here only goes up until 2021, but it just shows the green line there, private investment in fusion. So a lot of money pouring in, over $5 billion invested in 40 plus private fusion companies, including General Fusion, which Michel is of course part of. I think there's 20 or 30 private fusion companies in the US, and then there's a bunch more that are scattered around the world, and there seems to be new ones propping up on a weekly basis. And you might say, well, that seems wasteful, but what this allows is for fusion to be pursued in multiple different ways. Michel showed his approach, or their approach at General Fusion. There's a ton of other ones. Basically, there's magnetic on one end and inertial on the other, and there's an entire spectrum of approaches in between. And this allows us to get more shots on goal, reduce the risk, increase the likelihood of us succeeding. So it's tremendous progress, and again, a fundamental shift. Bloomberg has it estimated as a $40 trillion industry if you look at not only kind of fusion and the energy that it sells, but also the supply chain that needs to enable it. Just a list of some of the investors in fusion: Bill Gates, Sam Altman, Peter Thiel, Google, Jeff Bezos, a lot of big names, and they kind of see this as the future. A lot of these folks want to get ahead of the curve on this, and I don't blame them. So what has changed? What has made fusion investable? Why is it no longer just solely focused in the private sector, or sorry, in the public sector in these programs, and why has it come to the private? This up here, you see that it's called the Sharpe ratio. Very simple. It's what investors use to determine, if something's worth investing in. The higher the Sharpe ratio, the better. And simply put, it's the return over the risk. And what has happened is the risk has gone down in fusion. This is for a number of different reasons, and I won't kind of cover each one of these, but the main things has been technological improvements. There's HTS tape there, high temperature superconducting material that you see on the right there, which allows for magnets to be made that can reach up to, I think, 20 Tesla, which is considerably stronger than what's used on ITER. So there's the most well-funded company, Commonwealth Fusion Systems, basically built their company off of this magnet being available, or this material being available, and they can develop a machine that is orders of magnitude smaller than ITER, and is a lot cheaper and something you can iterate on a lot more quickly, and it requires a lot less time. So we don't need this mega multi-nation project to be able to achieve fusion. You can do it in a lot smaller scale, and they're even smaller than that. There's companies that are expecting or trying to build fusion reactors that can fit in a warehouse, which is very, very small relative to ITER. So that's kind of one of the biggest innovations, but better lasers, organizational improvements, with a lot of people actually leaving ITER and public programs because they want to see fusion achieved, and they're realizing that that's not the way to go. They're coming into the private sector, and they're coming with their ideas that might differ from what they were, I shouldn't say forced to pursue in the past, but what was kind of the main line. So a lot of positive, and of course the urgency of this problem has made it more investable as well. There's funds out there that are funding clean tech initiatives. This, I won't go through this, but basically on the x-axis, or sorry, the y-axis here is NT tau. Basically, you need, in order to achieve fusion, you need density, you need temperature, you need confinement time, and you'll see across the x over time, we've been getting better and better. And the NIF shot that Michel alluded to isn't on here, but it's kind of even further up than I think it's just above spark there. So we're getting closer to having kind of net energy gain. So what this has resulted in is not only private investment, but countries, governments have now put in place private fusion strategies. The UK has actually been a leader on this. In 2020, they announced theirs, aiming for public-private partnerships. And the US followed suit in 2022. The White House announced the bold decadal vision, basically trying to achieve fusion within the decade. And this has informed a number of programs, public-private partnerships, one of which was just announced, the milestone-based program for $46 million a week or so ago, a couple weeks now. 8 different companies that they funded. And they're really encouraging their national labs who have historically focused on fusion to partner with the private companies to help support them. Japan, which is an interesting one, of course my company is from Japan, traditionally a very conservative country that has been very much ITER focused, but has recently become interested in private fusion for a number of reasons. One, they see it as an industry that is going to blossom in the coming years, and Japan has a lot of technology that can help support it, and of course that's kind of why a company like ours exists. And I'm hoping that Canada can be next, and I know Axel wants the same thing, and I hope a lot of the folks in this room want Canada to get involved in some way to be there when as fusion grows. So fusion devices, as you can see, I mean, these timelines aren't completely accurate, but as you can see, the public programs up top and in ITER at the very top, their timeline's a lot longer, and you can see down below, companies have a lot shorter timelines. They're iterating a lot more quickly, kind of taking that SpaceX approach, willing to fail, and trying to find a path forward. And the truth is that the majority of these companies won't survive and become commercially viable, but that doesn't really matter as long as 1 or 2 do. That'll help save humanity. So I hope I'm not too far over, but I'm just going to give some insight into what Kyoto Fusioneering is doing, hopefully inspiring some of you folks that this isn't just a plasma physics endeavor. There's engineering involved, and again, Michel mentioned that, and I'll talk some more about it. But our company was founded in 2019. It's spun out of Kyoto University. We've got about just over 90 employees now. We've raised about 90 million, and so not only is there a need for this, there's a willingness for investors, and these are Asian and Japanese investors, which are even more conservative than the North American ones. And we're in 3 countries. We've got 2 offices in Japan. We're in the US, in Seattle. That's where I'm based, although I'm from Vancouver originally. And we've got an office in the UK. So global presence, and the reason for that is because the role we play in the industry is we're not focused on the plasma or the fusion reaction in the middle there. We've got 3 different divisions. We've got plasma heating with gyrotrons. So as Michel mentioned, to get the plasma up to hundreds of millions of degrees. And so we've got ECH heating to do that at frequencies in the 170, and we're kind of reaching up into the 230 gigahertz range. And then on the right side, the fuel cycle and thermal cycle, getting the heat out of the reaction, translating that into electricity, and the fuel cycle, getting the fuel out of the reactor, cleaning it up, storing it, processing it, getting the tritium out, and then refueling the reactor. I think roughly 5% or even less of the fuel is actually burnt on the reaction, at least in magnetic confinement in the tokamak. And so there's a need for very efficient and quick processing of your fuel and tritium extraction. So that's the role we play. We basically assume that it's very complementary. We assume that there's going to be a company that's going to have a successful approach to fusion. We want to make sure that all of them have the support from someone like us to basically allow their approach or their concept to reach the maturity, or as mature as it can get. And so we're there for that, and we want to make sure that we are working in parallel with these companies. If we had all the time in the world, we could work from the plasma core out and figure out these systems later on, but we don't have all the time in the world, and so it makes sense to work in parallel, and that is why we exist, and that's why we're in the US and in the UK, because we need to be close to the fusion developers to make sure that what we're building aligns with what they're building. So as I mentioned, there's industrial capabilities in Japan, and I think Canada has a lot to offer on this front as well. Maybe not in this, it might not be exactly what Japan offers, but Canada has its own strengths, which I'm sure we'll get into. But this is kind of how Japan has come to the playing field here. They've got industrial capabilities that are unparalleled, and we as Kyoto Fusioneering are kind of the window into that, encouraging those companies or we're offering designs for certain systems and then encouraging them to build those components and systems based on our designs. And then we work with our quote-unquote clients or partners to incorporate those in their fusion power plants. One facility that we're building right now in Japan, it's called Unity. It's basically an integrated test facility for our thermal and fuel cycle, basically trying to look at take our systems above the lab scale and test them in fusion power plant relevant conditions. Michel alluded to a lithium lead loop, so that's what we've got, and we're getting it up to 1,000 degrees Celsius because that's the temperatures it'll run at. Working on the heat exchangers, getting the temperature out, and converting that into electricity. So that's part of what this facility will demonstrate. We also just announced a partnership with Canadian Nuclear Laboratories. I mentioned Canada has a lot to offer here. And one of the main things is tritium. Canada has been handling the CANDU reactors for quite some time and has tritium expertise that the world needs. That is the fundamental, or one of the fundamental fuels going into these fusion reactions or fusion power plants. As Michel mentioned, you would like to breed tritium, so your deuterium tritium fuses, you get the neutron that interacts with lithium, that'll breed you more tritium, but the startup inventory, you can't just get there from nothing. You need tritium to start up your reaction, and with the number of reactors planned going up, the amount of tritium that's available in the world is going to be an important factor, and so Canada has a lot to offer there. And basically our collaboration with CNL is to take our fusion systems and technology, their technology that relates to tritium and tritium extraction from water and air and such, and bring those two to the market, so in some sort of collaborative fashion. So that is my presentation. Again, my name is Bibake Uppal. If you guys have any questions, ask them during the panel or come see me afterwards. Thanks.
Thank you, Bibake. You'll appreciate how difficult it is to put so much material, so many different thoughts, so much complexity into 15 minutes. So that turned out to be a little longer, but that's just fine. So thank you for that. So our first two panelists spoke about fusion. Our third panelist will speak about fission. And it is Igor Pioro, who is a professor at Ontario Tech University. And we thought it might be interesting to have both presentations on fusion and fission in the same panel so that you can compare and you can contrast. You see some similarities and you see some significant differences. So I'll call on Igor to give his presentation. And somebody has to bring up the slides for you. So.
Thank you very much. Yes, it looks like it's here. Good afternoon. I have quite difficult task, and first of all, from our bright future, to go to our thin Earth and to tell about nuclear power plants and severe accidents and everything what we have, more or less complete mess. Well, I'm telling reality, correct? No, I will not spend time on the content. Let's go to the top of the top. What we have here. General statement is well known that electrical power generation is the key factors for advances in any other industries, agriculture, and level of living. Also, it's very important for country independence. The best or worst example will be Ukraine, which has more or less oil, gas, nuclear fuel coming from Russia, which is currently disappeared due to Ukraine in a very, very bad position. No, Germany in the same way rely heavily on Russian gas now, no gas there. To the left, what we have, this is graph. HDI is Human Development Index. It's official parameter by the United Nations. Formula at the bottom, it's cubic root from three things. Life Expectancy Index, Education Index, and Income Index. I have plotted all 189 countries there, and the lower log scale, it will be electrical energy consumption, watts per capita in each country. 4 groups, very high HDI, green, high HDI, blue, medium HDI, yellow, and low HDI, it will be mainly countries unfortunately, in Africa. What I would like to say that, you know, countries like Iceland, small country, 340,000 people, they heavily rely on 70% hydro and 30% wind. Geothermal, Iceland. They have the highest EEC, it's around 6 kilowatt per person, because they more or less have free energies. Number 2 will be Norway, 70% hydro and 30% wind. They have 2.8 kilowatt per person. Number 3, our Canada, because we heavily rely, as you can see on this graph, we rely around 60% on water resources, on hydro, in the country, eventually. If we look at the countries at the bottom, for example, Chad and Guinea-Bissau, 2 watts per person. This is dead end. You can do absolutely nothing. You cannot teach, you cannot have agriculture, modern one, you cannot have industry, nothing. And if we count that this 2 watts per person mainly delivered to embassies, government offices, eventually whole country using candles. I have been in 6 African countries, I will tell you that this is absolutely true. At night, it's absolutely darkness, only candles in the streets. For example, of Freetown, Sierra Leone. How we generate electricity? World heavily rely on coal. Number 2, gas. Number 3, hydro. Number 4, nuclear. Unfortunately, due to Fukushima Daiichi nuclear power plant the severe accidents, we lost 4% in world generation of electricity. It is a very important point. I don't want to predict anything, but I will tell you, if we will have another severe accident, nuclear power can disappear from the world. And I have data to show that. Largest country by population, China, heavily rely on coal. India, 71% rely on coal. United States, the most developed country in the world, heavily rely on gas and coal, no, also nuclear, around 20%. France is #1 country by using nuclear. Unfortunately, before they had 78%, now they dropped down to 70%. But still, President Macron said that they will continue that. No, Canada, I have mentioned. In Canada, of course, the most nuclear province is Ontario, from which we are. 18 reactors, 3 large nuclear power plants, and we have 60% of nuclear electricity generation in Ontario. Bruce nuclear power plant, if you don't know, it currently is the largest operating nuclear power plant in the world with 6,300 megawatts electrical. Before us, we had Kashiwazaki Kariwa, but due to Fukushima Daiichi nuclear power disaster, from 54 reactors, they dropped to 33, from which from 2 to 9 in operation. What is interesting is only pressurized water reactors. No boiling water reactors in operation yet, within 12 years. No one in the world except Canada, at Darlington, no one building boiling water reactors as of today. Everybody is scared because it's happened with older designs of the boiling water reactors there. If we look at major advantages of nuclear, concentrated and reliable source of almost infinite energy, which independent of weather conditions, more or less is true. High capacity factor is achievable. Essentially negligible operating emissions of carbon dioxide. We're talking about full cycle, from extracting uranium ore to demolishing nuclear power plant. Because we have, but it will be around maybe the lowest one compared to other things. And a relatively small amount of fuel required. Now, of course, we have to be honest and say about the efficiency challenges, which we need to address in next generation reactors. Still, reactor generating radioactive waste and storage of them safe and reusing them is an important task, have relatively low thermal efficiencies, up to 43%, because all current nuclear power reactors connected to very old Rankine cycle. Nothing new. Subcritical pressure due to maximum, this is what you can get from any types of reactors. Compared to 62.5 for gas-fired combined cycle power plants, gas turbine and steam turbine, Brayton cycle, Rankine cycle, they can go to 62.5. No, in simple words, it's, if we will take 62.5, means 2/3 of energy introduced by gas combustion transferred into electricity, 1/3 thrown into environment near the plant. For nuclear power plants, it's opposite. 1/3 transferred into electricity, 2/3 thrown out near the nuclear power plants. And we need to change this trend. Risk of radiation release during severe accidents and production of nuclear fuel, of course, is not an environmental friendly thing. This is a table. Currently, in tables I have comparison what we had before the Fukushima Daiichi nuclear power plant. It's the latest, the third one, severe accident. In total number of reactors, we lost 3, was 444. Now we have 441, but new reactors, larger capacity, use capacity increased. The largest group and the group which mostly developed right now in all countries in the world will be pressurized water reactors. Light water pressure vessel, no boiling there. You can see 309, and to the right, how many will be built? 38 under construction, 36 possibly will be built. There is some plans for that. Number 2, boiling water reactors was 92, dropped to 60. It's definitely not very good trend for this particular reactors. And only 2 which will be BWRX 300 with 300 megawatts electrical, which currently started construction at the Darlington nuclear power plant. Number 3, pressurized heavy water reactors, mainly CANDU reactors, Canada deuterium uranium reactors, slightly dropped, but not much. Still we have some future, but it's not so significant compared to pressurized water reactors. 5, definitely, but all these developments mainly going to India. We sold them 2 reactors, I think that almost for free, because sanctions from the United States cut during when Indira Gandhi and government developed nuclear bomb in India. It was, always related to military applications with these things. And they developed their own pressurized heavy water reactors. We have very old, but the most efficient plants, it will be gas-cooled, advanced gas-cooled reactors in United Kingdom, carbon dioxide cooled, but all of them will be shut down because for 35 years, no developments there. Due to, I don't know, they have only 1 pressurized water reactor, due to UK possibly will be left without reactors. EDF, Electricity de France, building 2 reactors, but it's long-term building. I'm not sure when they will finalize that. We have 2 newcomers. It will be gas-cooled reactors. It's small modular reactors, second set of small modular reactors put into operation. It's helium-cooled, helium considered as future nuclear reactor coolant compared to carbon dioxide. It's only 100 megawatts. Also, it's not bundle design of fuel. It's a spherical fuel, 6 centimeters in diameter, in graphite matrix nuclear fuel there. It's very, very unique things. They started last year, March. Due to this, definitely we need to get more information how they will perform, because it's absolutely unique there. And we have also 11 left light water cooled graphite moderated reactors. 1 of them exploded in Chernobyl. Due to this, they will also gone. No one will build them. And we have unique reactors, will be sodium cooled fast reactors. It's only 3, 2 in Russia, 1 in China, built by Russia. This is what we have more or less in general for all types of reactors. By countries with the largest number of reactors. In red, number of reactors decreased after Fukushima. The most significant loss is in Japan, 21 reactors left. From 54 started to be 33. Now here we have no Germany. Germany closed, shut down 3 last reactors in April. It is unfortunately Germany started many of these things, and now they are out of competition. Who is the front runner? front runner is China. In 12 years, they put into operation 44 reactors. It's more than the whole world. It's really, really amazing. It's real renaissance. It's not like anywhere else. For United States, trend, they shut down reactors slowly, one by one. They only put one new reactor just several weeks ago, AP1000. They put in second one and nothing else. Their trend to extend operational term. They have 6 reactors for 6 years extended, and I think there's 8 reactors for 80 years. Now, of course, we have to understand it's easier to say that they will work for 80 years right now than really to reach this level, because we have many reactors which never, after construction, never were put in operation or shut down in just a couple of years. Next one, it will be all countries with nuclear power reactors. Yeah. And I will not go in details. In green, they're building reactors, or they have reactors and they will build new ones. In red, they have reactors, but they will not build the new ones. Eventually, we have 32 countries with operating nuclear power reactors, 3 countries building nuclear power reactors. However, 14 countries with nuclear power reactors don't plan to build them. Now, this is similar to what we have the previously. 2 countries in the world, they're leading the number of reactors built. It will be Russia and China, 32 in total. China 30, Russia building abroad, China building inside country. However, with latest sanctions against Russia, I am not sure that they will be capable to deliver such a large number of reactors. The rest is India, 11, and many other countries is significantly less. This is impact of 3 severe accidents. The major one, or the largest one, it will be Chernobyl nuclear power plant. You can see that within 5 years, almost 120 reactors have been built. Chernobyl happened, by inertia still continued, after that dropping down less than 40, less than 20. Now we are approximately at the level of 1975, 1979. You can see what had happened, how one huge accident affected the whole industry there. Here is, yes. Driving force for currently in all nuclear reactors and thermal power plants is thermal efficiency. You can see on the top different plants. As I said, maximum from reactors we have 43. In blue, light water-cooled, heavy water-cooled reactors, and you can see from 26 to 38% efficiency. Now this is what means Rankine cycle. Small modular reactors is very hot topic today. We have counted 108 concepts, but I would like clearly to say that it's vast majority concepts. You cannot expect that these things will be soon built. Only 2 concepts in operation. Pressurized water reactors on the barge, 2 of them in Russia, and 2 Chinese helium-cooled reactors there. Due to expect that all 100 concepts will be put into operation, it's absolutely impossible. I can expect maybe 6, 10 concepts, but not so much. And some of them developed by universities. I can understand this is a great interest for students and everything, but university never can design a reactor. It's impossible. Largest countries by current concepts: United States 27, Russia 15, China 13, and Japan 12. There is a common misunderstanding that small modular reactor is something very simple. 1, 2, 3, and we will be done. This is example from Russia. This reactor operated at submarines for a long time. They put on icebreakers, and after that they decided to put into civil engineering on the barge 2 of them. It's only 35 kilowatts. In red, this is what they have to add passive safety systems. Otherwise, you cannot do that. And it took more than 10 years for already operating, trusted, and in industry proved reactors. Now this is to the left, this KLT-40S. Central cylinder is pressure vessel. Green ones 4 circulation pumps, reactor coolant pumps, and gray is steam generators. They have another one also coming from possibly submarines and icebreakers, Rhythm 200M, it's around 50 megawatts. What they have done is very unusual design. They put steam generators inside pressure vessel. With this, they increase thermal efficiency by 5% without anything else, not changing any other parameters. No, also we have to understand smaller core, you have to enrich higher uranium. It's detailed, but I will bring your attention to that. Russian reactors, 19% enrichment, very close to the limit of 20% by International Atomic Energy. Due to this, also not many countries allowed to enrich uranium. Also, I am not sure that we have treaties to supply enriched uranium to such level to other countries. Due to this, it's still very gray area what we can consider. So this is Barge to the left. Idea is in operation from December of 2019. Idea, for example, to bring such barge with desalination unit to Middle East. It's very profitable. China going by this way. Some other countries moving to that because this ship belongs to manufacturer country. You don't need to have special laws for that. You bring, you take it, you bring new one, and it's operating. So this is a helium-cooled reactor with spherical fuel. This is thermal efficient generation 4 reactors. We have 6 concepts. All of them high temperature reactors. 2 of them in operation. It will be sodium cooled fast reactor and very high temperature reactor. It's helium cooled in China. Now this we already discussed. I will not spend time. Just I will say that links between current reactors and future fusion reactors. First of all, as I mentioned, that CANDU reactors can generate tritium, which is important. Power cycles should be considered, which is proven already in current industry. Safety, including passive safety systems, and highly qualified personnel we also need to train. And this is, thank you very much.
Okay, thank you, Igor. You will appreciate that both subject areas, fission and fusion, are complex. You can easily get overwhelmed by details. And I don't want you to do that. Right? So, but I think the answer isn't just how do we simplify. I think the answer really lies in how do we understand the fundamentals and how do we build on the fundamentals. So I'll give the members of the panel an opportunity to maybe respond to 1 or 2 questions that I would like to pose, but then I would really like to pose the questions to the audience. One question I'd like to pose both in respect to fusion, to both Michel and to Bibake, is the role of universities in the development of fusion energy as an energy source. And you may want to reach beyond it and also look at how we would use that energy other than for our conventional purposes. So I know, Michel, you've been reaching out to some universities in Canada. Can you comment on the role that you see for universities in engineering and fusion development?
All right.
I'm making the assumption that you can actually hear me.
Yeah, I can hear you.
Okay, good.
University, I see 2 roles for university. The role number 1 is to actually train people. Like the industry will actually require nicely trained plasma physicists and diagnostic and engineer to run all this machinery. To design and build that, we need trained people. So we do like laboratory that have a fusion, like a fusion lab and a fusion department. And then we've been hiring, for example, here in Canada, there's a university at Saskatchewan as a department that do fusion, and we have hired many people from there. So people, first thing. And the second thing is to actually do some work. So we have been subcontracting some parts of work to different universities. So for example, we have a collaboration with McGill on the fluid dynamic of our imploding fluid. So they're doing some simulation and some theoretical calculation on that. So we can use university to do some works, and we can hire people from those departments.
Okay, thank you. Bibake, would you like to comment as well?
Yeah,
Because
so
you are a spin-out from Kyoto University, so.
yeah, no, I would echo Michel's comments, and I wrote down the same ones. Fundamental research, a lot of the capabilities and know-how in the universities, national labs in the U.S. play this role. The next generation of talent. The other one that I would add is generating new ideas in companies spinning out, right? The supply chain and the ecosystem for fusion is going to go beyond the fusion developers or companies like ours, there's going to be a larger ecosystem that needs to develop. And as you can tell with a lot of the companies that are in the private fusion sector, many of them have spun out of universities, which is where a lot of ideas get generated. So that would be the third one I would add to the list.
Okay, so very good. So the development of expertise is really important. The development of ideas is really important. I would offer you the suggestion that we really do need ideas about separating the constituents of the partially burned fusion fuel, because the conversion is nowhere near 100%. So you have to separate and you have to recycle. And that's quite difficult to do using current technologies, which are based on, and we heard a little bit about that, on absorption, cryogenic distillation, electrolysis, quite complex. And it begs the question of what might be quite fundamentally different ways of doing it. And I think there are some ways that we can look at. Okay, so that was a question to universities. Igor, do you want to say something about universities and fission development?
Well, I would like to say that eventually we have, mainly in Ontario, our university, we have Department of Nuclear Engineering, created from the beginning, from 2003, as university exists. We have the largest group of professors, around maybe 15, 16. We also have a group of professors from university in Hamilton. Yes, McMaster. They even have research reactor to do this, but I think that under the physics department umbrella. Also, we have other professors working in different areas. Unfortunately, we have lost nuclear professors from Quebec, because Quebec shut down a number of years ago the only one reactor which they have, Candu reactor. They have a lot of hydro resources because they decided not to proceed that. The major problem is that, of course, if you lose expertise, it's not easy to restore. It's easy to lose, but not to return back. This is what we have. No, eventually in the summer, maybe 2013, 2014, we were the largest nuclear engineering school in North America with 550 students. Right now we have less, but definitely we have great capabilities. The problem is that everything depends what will happen with nuclear power plants nearby. We located approximately 15-20 kilometers from Darlington and 15-20 kilometers from Pickering, and maybe 200 kilometers from Bruce. I don't know, Ontario Power Generation, who owns Darlington and Pickering, they decided to shut down a number of reactors for Pickering because it's first ones, long terms. And of course, students cannot see the future. Due to this, it's very sensitive what will be. It's not like regular. Of course, program is great. It's close to mechanical engineering with some extra things. But usually students, why they have to go to nuclear if possibly no works, let's go to mechanical, which will be definitely more works. I
think that's probably sufficient. I know that there are some hands going up, so would you like to pose your question? There is a mic actually, because it's quite a large room.
Actually, I have several questions, but maybe I'll ask one for now. Maybe if I could ask Bibake, but it also, Igor mentioned it as well, the coupling with the nuclear power plant, the electrical generation plant is a very important aspect. And right now, just using the Rankine cycle or steam cycle, or even perhaps the Brayton cycle, efficiencies are very low. Do you have some suggestions, innovative suggestions on how we might be able to avoid the Carnot cycle and the limitations in efficiency? Because I think there's a really good point that was brought up that, you know, it's clean, but the efficiencies are very low. Yeah. So I'd love to hear what innovative ideas you have.
I think that Carnot theorem is fundamental. We cannot do anything. What is the temperature? This is defined as the thermal efficiency, theoretical one. We never can reach that, but we can go a little bit closer. The ways which we are considering for next generation reactors, it can be combined cycle, or originally they planned helium turbine and subcritical pressure Rankine cycle at the outlet of the turbine. But I don't know how it's happened. When they had small gas turbines, it was okay. When we started to do large ones, there is a phenomenon as ingress of helium in bearings of gas turbine. They started to be brittle. And now this idea dropped down. Yet still we have to go through heat exchanger. On another side, for example, 80% nitrogen, 20% helium, and also combined cycle with gas turbine. Or we can go as thermal power industry done in 60s to move to supercritical pressure Rankine cycle. The problem with that materials, we don't know which materials can be used. We have high neutron flux, never tried that. And of course, high pressures. Usually should be 25 megapascal compared to current 15, 16 megapascal. It is quite challenging.
Okay,
Could
I think you
ask
have a follow-up. Yeah.
One quick other question. What about, for example, thermochemical cycles, like, for example, producing hydrogen? Would there be any benefits in efficiency there?
Yes, no, number one from Gen 4, which is concept under development, is very high temperature reactor with planned 1000 degrees. Yet as we can link the high temperature hydrogen electrolysis, and we can get at such level, I think it's 850 degrees required. At the lower level, we can use through thermochemical cycles. Our university developed for quite a long time copper chlorine cycle, which will be maybe approximately 550, 600. But it's not a simple question. First of all, we really have to have customers who would like to have hydrogen. If it will be cars, I can understand, but currently more or less everybody moved to electrical cars and with very few ideas on hydrogen. It can be done and it's considered. But currently I have not heard that any nuclear power plant connected to hydrogen cogeneration plant.
But it's a very fruitful area to look at, that conversion of energy that comes from a fusion machine into electricity. And going through a medium such as steam is only one way of doing that. Okay, I think I have a question on my right. Yes?
Thank you. I've believed in fusion power for 50 years, and I do hope I get to see it in its commercial rollout. For general fusion, I'm a little confused. How do you compress a plasma with walls encroaching? Don't the walls just cool the plasma? And you say liquid lithium, great, but all liquids have a vapor pressure, and plasmas are struck in a vacuum. How does the lithium just evaporate into the vacuum? So 2 questions there.
Okay, the vapor pressure of lithium at 350 degrees C, which is the lower temperature when we replace it, is 10 to the minus 7 torr, which is sufficiently low for operation. So the vapor pressure of this particular liquid is good enough. The end of the question is that all the wall come in and touch the plasma and kill it. Well, actually, it's not exactly how it happened. The plasma is, and when you compress it with a liquid metal, which is a conductor, you induce current in the conductor, which push the magnetic field in front of it. A bit like the idea of the superconductor magnet floating on top of a piece of metal. Because we go fast, there is some permeation, like there's some diffusion of magnetic field, but we're going at the speed in such a way that the magnetic field does not have time to penetrate into the metal. So what you push in front of the metal is the magnetic field, and the plasma is in the magnetic field. So you do not touch the plasma with the wall.
Oh, thank you.
Okay, Robert, did you have your hand up? Or? Yeah, the mic is just behind you.
One of the interesting discussions I was having with Bob Walker, who's one of the fellows of the Academy, was around recent discussions, I think it was with the Canadian Nuclear Association, on what they called 50 by 50 and 90 by 90. So at the moment, if I recall, our total national capacity is about 16 gigawatts. And so what they want to do is to increase that by 50 gigawatts, 50, by 2050, and 90 gigawatts by 2090. I was not encouraged by Igor's slides. The 90 gigawatts is supposed to already include some level of fusion. And that number, the 50 and the 90 gigawatts, is supposed to represent 30% of the total national capacity. So I'm just having a little sort of cognitive dissonance there between that objective and what the current pace of fusion advancement is, and you were saying with ITER and the others, and what the global picture of what's happening with Gen 4 technology. So just a bit of a comment, but when we're talking these scenarios for net zero and nuclear being this big piece, anyway, just your comments on that.
I think this is a very valid comment. Even under the most optimistic projections of fusion development, where we may have several fusion plants, and let's even assume that they're at a single gigawatt, which is a typical plant. By 2050, we will not have enough in the world to make a really big difference. By the end of the century, that could be different. But in order to get to that point, you have to start. I mean, we can't just say, let's wait till the middle of the century and then we think about the second half of the century. So it's an evolutionary process. There are big hurdles to overcome. You heard some of them of a technical nature here today. There are financial hurdles to overcome. We mustn't underestimate the issues around social acceptance. Anything that deals with the center of atoms, namely nuclei, elicits certain responses. I mean, that's just the reality. Ron, I think you had a question. Do you have a mic?
Great, and my question's for the gentleman from
see
Kyoto
it.
Fusion, and that's regarding dispatchability and load following. So across North America, solar and wind are dominating investment in new generating capacity. Texas is going towards 50% solar. The WEC, we're seeing a lot of solar and wind in the Western system, and it seems to me the holy grail is around load following. And right now we've got peaking gas, we've got batteries, major investment in batteries in California in the last year. So what are the opportunities for fusion in particular to become a peaking resource? Thank you.
It's a really good question. Let me put it to Bibake and then to Michel, and then I have a comment because I've thought quite a lot about that question and the answer to the question. Yeah, Bibake?
Well, I'd be curious to hear your thoughts. I mean, if you've given it a lot of thought, I think the promise of fusion is to serve as the base load energy source, and so you're right. I think we're increasing the amount of renewables on the grid in order for them to. I mean, we need to build a lot of excess capacity for them to kind of replace the base load energy source. I guess the help me understand your question. So.
Is there an opportunity, because I think solar and wind are so cheap. They will win, and they provide energy.
Yeah.
And it seems to me what's missing in the picture to electrify everything is if that's actually a prospect, is those sort of peaking resources. So if nuclear can also provide peaking resources in addition to the base load, that's where I'm going. The ability to load follow and ramp up and down, or to dump load. So operating at the high, at the base load, which is at the same level as the peak, and then I guess dumping load when it's not being needed for, say, generating hydrogen.
Okay. Michel, would you like to comment as well from the fusion perspective?
Yep, I can comment. So the DC machine, like the tokamak, fusion is very tricky. You're going to have to achieve very defined condition to make it work. So a DC tokamak, it will produce a gigawatt, and it will not work at 900 gigawatt. It'll just be a certain big chunk of electricity. No load following possible. People that use pulse machine, like the laser fusion or general fusion that use pulse machine, the exact pulse will have to be exactly the same and very finely tuned, but we can constantly change the pulse rate. The general fusion can be capable of load following. The laser fusion guy will be able to load following. However, fusion has zero cost of fuel and large cost of the machine. So economically, it's better to run your machine at full bore because there's no cost to the fuel, and there's a large, like, this fuel machine, they're gonna cost a lot of money. They ain't gonna be run cheap. So the capital cost is high, the fuel cost is low, which economically, it means that you're better to run it at full blast. But pulse machine will be able to follow, but it's not gonna be very economically desirable to do so.
Thank you, Michel. Ron, I think you have a question,
Yeah,
or a comment?
a very simple question. I heard in 2 presentations the quote, almost infinite source of energy. How is the release of a almost infinite source of energy likely to affect the global warming?
Okay, so if we convert very large quantities of mass into energy, what is the consequence of that? Right? Well, so you have to take, okay, I can have a go at it. You have to take a holistic view because the Earth certainly radiates into outer space on account of Boltzmann's law. And the outer space is infinite, essentially. So as long as we don't have a highly heat-absorbing atmosphere, we should be able to keep, as a first-order approximation, the temperature of the atmosphere and therefore the climate in check. So I think that's the first order approximation to think about.
That's kind of
holistically.
an answer.
Right?
Okay.
If I can.
You want to add to it?
I want to keep us on schedule here.
Yeah.
We have events at the following events. So
By the bell.
I just wanted to thank the panel for a very interesting and informative discussion, and I just love it when you feel that you're actually getting close to seeing the real data, seeing the real issues, and seeing the problems that the engineering community, a whole generation is going to have the pleasure of working on. Yep. So
we'll talk about it during the coffee break.
And we'll do that. Okay, so thank you. Coffee is outside. If you can be back in 12 minutes, and we will keep ticking along.